Good morning. For this beam theory problem, we complicate things a little bit more. So we have a cantilever beam, but the complication comes from this fact that the distributed load is triangular at this time. It's a little bit more work for us. The first step, like usual, all the three steps are the same. We calculate, in this case, support reactions, and we have for this triangular distributed load that you can see there, it's negative. We use Newton's second laws to figure that out. We have those reaction here in the at the left. So basically, it's simple. The only thing is the idea that being a triangle where the centroid sits, it's at 2/3 of the length of this from the tip of that triangle, or 1/3 from the base, however you are considering it there. So then, having the free body diagram built, then we use it to build a shear diagram as we are doing it here. The left side, we focus on being shear diagram, shear force. Basically, we focus on the concentrated loads, concentrated forces, in other words, not moments at this moment. We at this point y, we can see that tells us that we need to jump upward with the amount W naught L divided by 2, which we do right there. And then we have to look at that differential equation here, and we can see that W is not constant anymore. It has a negative sign, which I put it here, and you also see that its magnitude keeps decreasing as we move from left to right. That means that the slope of this shear force is supposed to be negative, and it keeps decreasing, not constant, not a line, in other words, because here it was constant, and now that was this, basically it's when we take the derivative of that, basically it would be a parabola. So I mean, the curve that builds it's a parabola. If we integrate basically v here, we are supposed to get a second order polynomial. I put here it's a convex one, and the reason I put it, if you look here, we have two variants as we discussed previously. You have this option that I did with the red, and the other one, the option. But if you are drawing, if you have a little bit, you're in trouble, which one should it be, which is correctly, then keep putting points. Take a point there and put a tangent to see, and take another point and look at the tangent. What happens? Is the tangent increasing or decreasing? That's the slope basically. And as you can see here, we start almost horizontal, and then which is here basically it's not necessarily horizontal. It has a W naught value there, which is different than 0. Then we keep, as we move forward there, the slope of that curve will keep increasing, which is not our case. So that, concave parabola, it's not good here for this situation. So it has to be the other way around, which is when we take in any point, you put a slope, we can see that it's the line is negative, as we said, the tangent, but it will keep decreasing, which is our case. And by the way, when we reach this point, W is supposed to be 0, so the slope is supposed to be horizontal right there, 0 slope. And the question is it sure? Yes, you can, if it's not, you can calculate it. If you're not convinced by that, you can calculate the change with the change from point A to point B by using this the area. The change will be, when we integrate that equation, it's going to be the area of this triangle that I put here with yellow. So easy to calculate. Again, don't forget about the negative sign for W naught. It's pointing downward, not moving upward. And then when we have that W naught L divided by 2, that was in point A, then minus that one, it's going to give us 0. So this is our shear diagram. It's positive and its magnitude keep decreasing as we move forward. So we use that shear diagram to build in the third step the moment diagram. Again, this time we start looking at every point. Am I having a concentrated load? And yes, we have a concentrated moment in this case there. That's because we work with moments. We focus on them, concentrated moments. And then we can see that this is counterclockwise. As we said, this is negative. That means the jump going upward with the same value that it had when we calculated the diagram, the free body diagram. And now there is no other concentrated moment in this beam. So in that case, we focus on this equation to see the change from left to right. We focus when we look at that, like for the sign of the shear force and for its magnitude. The sign is positive and the magnitude keeps decreasing. So the slope for this moment, function should be positive and keep decreasing. Again, it's not going to be the other way. Again, this is not a parabola, by the way. This is a parabola. This is a cubic function. I forgot to mention it here. I did mention there. But it's a cubic because the polynomial this time is third order. That was second order. This is third order. Although it looks like, like a parabola, I kind of drew it in that way. But don't forget, it's a cubic function. This time, of course, at this moment, the shear force, its value is 0 there, so the slope is supposed to be 0. But what's going to be the value of the moment, not the slope? We don't have any concentrated moment there. But if suppose you will have a concentrated moment at this location, definitely you will not end up in 0. You'll end up here with some value, and that concentrated moment will bring it to 0. If it was supposed you have a concentrated moment that is clockwise, will be positive and will push it to 0. But of course, that will be the value of that concentrated. You can look on the other side and start looking, and that value will be negative value. You will end up with a negative value exactly of that moment. But you can also, like I did, for example, it's harder to, calculate in the previous, we did calculate the area of this curve, which in this case is not a triangle, not a rectangle, so it will be being a parabola. I need the equation for that, and it's not so easy. So another way, other than looking here, what's happening there with moments, like we said in the right side, that's probably the simplest way. Another way is to use the free body diagram and write the moment, all the moments there from left with respect to point B. So everything in the free body diagram, which I have to add that, basically replace that W naught with the resultant and locate it at the centroid there for that triangle. So when we are applying like this a Y, I'm getting this as a positive there, and this is going to be negative moment. It will rotate. This is also negative. So basically, I end up with 0. As you can see, 3 minus 2 minus 1. When I bring everything under that common denominator, and then it gives us a moment 0. Again, multiple ways to skin a cat. In this case, like we said, easiest is to look at right here. Even if you would have a moment, concentrated moment there, that is supposed to be opposite to that one, to bring it to 0. So basically, in that case, we will still end up with that value here that will make a positive jump upward, because it's going to be in the clockwise direction. Thank you for putting up with me, and I hope if you have comments and questions, please put them below or send me an email. And I hope you have a beautiful day.